I'm Alessandro di Federico. I'm a PhD student at Politecnico di Milano. And today I'm here to talk a bit about libtcg, which is a project to expose a certain part of QEMU, particularly the front end of the tiny code generator, to external tools. But let's dig into it. So first of all, when I started to get into QEMU, I thought it was kind of a cool project, okay, right? The basic is just a dynamic binary translator. The idea is that you have a program, you go to the entry point, you get the program counter, you load the code that is at the corresponding address, and you start to translate the assembly instructions that are there into what are called tiny code instructions. Tiny code instructions are basically very simple instructions which have no side effects. So one of the main characteristics of instructions, for instance, of x86, it's that when you have an addition, it doesn't just perform the addition, but it also, for instance, sets the carry flag or the overflow flag or whatnot. What the tiny code instruction do is basically they expand completely the behavior of each single instruction without any side effect. And then from this intermediate representation, we could call it, you translate it to assembly to code that can be run from your host CPU. So maybe your input instructions are ARM instructions and you want to run it on x86-64, then there is this translation going on. And I like this because my background is in compilers, and this structure pretty much resembles a compiler. You have a front end, which takes a language, in this case assembly code, it translates it into an intermediate representation, and then it compiles it back to another architecture. Pretty much the same structure of a compiler. And the nice thing is that QEMU supports a large set of architectures. Here we can see only some of them. And basically, from this architecture, we go to an intermediate to tiny code instructions, and then we have several targets. There are less targets there are less supported target architecture than input architectures because maybe you're not really interested in learning x86 code on, I don't know, Xcore or whatever. There's also an interpreter, which is TCI, in case you cannot, a certain architecture is not supported, you can just interpret the tiny code instructions. So let's see how they look like. So on the top here, we have a call instruction at address 0x2000. It's from x86-64, let's say, which is calling a function at address 0x2000. And below, we can see the corresponding tiny code instructions generated by QEMU. As you can see, we are writing a value 0x1005 into a temporary variable. And if you look at the following 4 instructions, that's basically a push. We are writing 4 in a temporary variable, tmp1. Then we are subtracting 4 from ESP, which is the register representing the stack pointer in x86. And then we store there at the ESP -4 the value 1005. And then we update ESP. So what is this? Who can tell me what's happening here? Sorry?
Just change the instruction pointer. And you push the return address.
It pushed the return address. So 1005, it's the next instruction after call, okay? Call is at the address 1000. In this case, the call instruction is 5 bytes long. So the return address, it's 1005. And we push it to the top of the stack. That's what's happening, okay? This is the typical calling convention of x86. And then the last instruction writes 0x2000 in EIP, which is the program counter. So it performs the jump. This is a simplified version, but this is the key idea. Expand completely the behavior of the instruction. No side effects. The other cool thing about QEMU is that you have 2 main modes of operation. I'm completely ignoring KVM. We're not talking about KVM here. The first mode of operation is the system emulation. So basically, you're emulating the full machine, including MMU, peripherals, and whatnot. So when you use system emulation, you can boot an entire operating system, a kernel, and things like that. But then there is another mode of operation, which is the user emulation. In user emulation, you can run a program compiled for Linux as is, okay, without booting any kernel and without doing anything like that. And we will, in this presentation, we will focus mainly on user emulation. So tiny code instructions are very nice, right? But I wouldn't implement all the possible operations that the various architectures have in tiny code instructions, okay? Think about the floating point division. to implement floating point division in C, it would require some tens of lines, okay? So doing that in tiny code instruction would be very cumbersome. So QEMU offers an alternative to implementing things in tiny code instruction, which are helper functions. So if you have a very complicated operation to perform, instead of emitting simple instruction, you can say, okay, just perform a call to a function that is part of QEMU that will make some computation, can touch the whole CPU state, and then return something. These are called helper functions. And they are also used, for instance, to implement the CPU ID, which does a bunch of things, or to implement sophisticated things like AES and I. And we'll also see about syscalls in a second. For instance, this is on the top we can see the tiny code instruction that performs a call to an external function called CPU ID, and we can see its implementation below. You can see that it reads some parts of the CPU state. You can see the EAX register and the ECX register being read, and then you can see that some other registers are being updated. Now, here the details are not relevant, but just so that you can get an idea of how it works. Okay, syscalls. We said that the user emulation can emulate only the operating system, basically. So things like process initialization, signals, and syscalls. So how do syscalls work in user emulation? Well, basically, suppose that you have a read syscall in your ARM program, okay? The identifier for the read syscall on ARM is this number. Its identifier goes in register R7, and the first 3 arguments of the syscall go in R0, R1, and R2. What QEMU does, it has a layer that simply translates this information from how you would perform this syscall in ARM to how you would perform it in x86. So for instance, the corresponding syscall identifier on x86-64, it's 0, and you use a different set of registers. The syscall identifier goes in RAX, and this kind of stuff. So the syscall gets forwarded almost as in to the host operating system. Okay, but let's focus for a second on the front end, okay? We said that this resembles a compiler, so let's first focus on the left part. It's pretty interesting. In particular, if you do binary analysis, so for reverse engineering purposes, you want to understand what a program does, maybe statically, this is known, the front end is known as a lifter. A lifter is something that takes assembly and lifts it into a higher level representation where each instruction has no side effect and that you can more easily elaborate and perform analysis upon. So this is very interesting from the community from where I come. So the idea is, can we expose this front end to external applications? And this is the whole idea of libtcg. Okay, making a library out of QEMU obviously poses some challenges because QEMU has not been thought to be used as a library, right? So first of all, we need to think about position-independent code, how to generate how to output the files and things like that. Then we'll have to design a decent API, an API that is simple and portable. And then we'll also have to think how to handle helper functions because those are interested too, right? First of all, we introduced 32 new targets. So when you do -configure in QEMU, you will see 32 new possible targets along with the system emulation for ARM and the user emulation for MIPS. You will have a set of new targets. And they look like this. They're called name of an architecture -libtcg, and each one of them outputs a distinct library, a distinct shared object that you can use. One of the challenges that we had to face was trying to link as little stuff as possible. Because for instance, if you're only interested in exposing the front end, you do not want to expose anything of the back end, right? The code generation part, if you're not interested in that, there's no reason to put it in the library. So we had to move some functions around to reduce the coupling between the files. And basically, if you're familiar with the QEMU code, we're trying to keep exclusively the CPU.c and translate.c files, which are those that contain the actual translation logic from the input architecture to tiny code instructions. And then, we removed helper functions because when you have to perform the translation, you're not interested in running them, okay? So you don't need to link them in your final binary. We removed the GDB stub and things like this. Then, as I said, we have to make a library out of it, right? So libraries have to be compiled as PIC, position independent code, so that they can be loaded everywhere, wherever in the address space. This is pretty simple to do in the QEMU build system. The only thing is that certain files in QEMU are compiled only once, no matter for how many targets are you choosing. So, for instance, certain C files will be linked in the same way. The same file will be linked into the, I don't know, ARM system emulator or in the MIPS user emulator. And so these files that get compiled only once, no matter how many targets are you trying to compile, how do we compile them? As PIC or not PIC? Currently, if there is at least one target, which is libtcg, we compile all of them as libtcg, and it's not super nice. We can work around that using libtool. Okay, let's quickly talk about the API. One of the key features that I wanted to have in libtcg was being able to load at the same time multiple versions of the library. So maybe at the same time, we want to be able to load libtcg for ARM and libtcg for MIPS, okay? They don't have to conflict. To do this, we decided to export a single function, okay? So your shared object, your dynamic library, exports a single function. This function is called libtcg_init, and it takes two arguments. The first one is the name of the CPU, which is, you might be familiar with this parameter, is the one that you give when you, on the command line of QEMU when you use -CPU. Then you give a guest base, which is basically the address where pages will be allocated from the guest point of view. And when I mean guest, I mean from, let's say, the program that you are translating. So you can imagine it as an offset. And then it returns you a data structure, pretty simple, which is the interface. So it returns you a bunch of function pointers. So basically, you can get a pointer to this function in several libraries. You can call it, and you get the interface as a bunch of pointers. So it's easy to load multiple of them and use them separately. There are three functions. They are all function pointers. The first one is mmap. The second one is the translate function, which actually performs the translation. And the last one is just a cleanup function. So let's first see libtcg_mmap. It's basically an mmap function. So you give it an address, a size. You can specify a file descriptor if you want to mmap a page from a file. You can give it read-write execution permission and whatnot. And it will return you two things. One, it's a pointer that you, as the user of the library, should use if you want to write in this page that you're mapping. And another pointer, which is the pointer from the point of view of the guest, okay? So let's say considering the guest base offset. And finally, you have libtcg translate, which just takes an argument, and it's the address that you want to translate. So let's suppose that you mmap a page, and you didn't ask for any specific address. You can say, okay, translate whatever it's at the beginning of that page. And it will return you a data structure which contains basically an array of tiny code instructions, but we'll see an example in a second. Since some of these data is allocated on the heap, then you have a cleanup function. So you just call, when you're done, you call libtcg free instruction, passing a parameter to the value that libtcg translate gave you, and you clean up everything. So let's see an example. So this is your external program, okay, your external C program. First of all, you perform a DL open. So you dynamically open load our dynamic library. In this case, we're loading the x86-64 flavor of libtcg. We use DLC to obtain a pointer to the libtcg init function, which is the only one that the library export, as I said before. And then we invoke it. We ask for QEMU64, which is just like the jolly CPU. We pass a guest base. Trust me, that's going to work. And then we have the interface. In the interface, as we said, we have three functions, and we're now going to use it. So let's first, in this example, we want to mmap a page, just an empty page full of zeros, and we want to write there, let's say, 4 NOP instructions. Whose code is 90, 0x90. So we mmap it, and we get back the address pair object, which, as I said, has the pointer from both point of views. In this case, it's, we mapped it in readable and writable. It's anonymous. It's not attached to any file. And then we simply perform a main copy of 40x90 into the address that we are supposed to use if we want directly to read or write there. So we use address.pointer. Then we want to translate what's there, so these 4 bytes, right? So we use libtcg translate, and we pass the other pointer, the one from the point of view of the guest, and we're done. In instance, we have the list of our instructions. And for instance, there's a field called instruction count, which will tell you how many tiny code instructions have been generated, and you can just loop over it. There's another field, instructions. There's the .opc opcode, which gives you the specific opcode of the instruction, so whether it's a call, a move I, or whatnot. And then in the end, when you're done, you simply free the associated storage. Okay? But let's now talk about helper functions, okay? If you want to do any kind of analysis, it's interesting to know that you are calling a certain helper function, but sometimes maybe having the code it's also important. Maybe you want to know what register that helper function touches, reads or writes, right? So how can we expose them? The idea is to use the code as a resource. So just, let's say, as a commodity. So the idea is to use LLVM IR. So LLVM is a compiler framework, which is, maybe you know Clang, which is an alternative to GCC. It's pretty popular for its IR, its intermediate representation, which is pretty simple to manipulate. That's one of the key features that made it famous. And the idea is, okay, why don't we take all the helper functions, we ask Clang to, instead of, to compile them, but instead of producing object files, or let's say real code, we ask it to output LLVM IR, to output modules. So for each helper function, for each helper module, which are usually denoted by blah, 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 underscore helper.c in the QEMU source code, we obtain an LLVM IR module. So high-level representation of what the helper do from a compiler point of view. And then we can also merge all of them, all the helper files, into a single module using the LLVM link program, which is basically the linker that you might be used to in C, but instead of working on object files, it works on LLVM IR. And then you distribute, you install in the target system this module that contains all of the helper functions. Okay, but why are we doing all of this again? I want to spend 2 minutes on rev.ng, which is my project, it's my thesis project, and I'm working on this. By the way, rev.ng is also the domain of the website, so feel free to visit it. It's basically a binary analysis framework. And at its core, you have a static binary translator. So while QEMU is a dynamic binary translator, it takes one basic block that you want to execute at a time and translates it to something else. Rev.ng does that statically. So you just look at the binary, you try to identify all of the basic blocks, you translate them offline, and then you recompile the whole thing in a standalone binary for another architecture, and that's supposed to work. So practically, you have ls compiled for ARM, you identify all the basic block, you translate all of them from ARM to, in this case, first tiny code instruction, then LLVM IR, and then you can recompile it back. Let me give you a better overview. So let's suppose that you have md5sum.arm, which is the md5sum binary compiler for ARM, let's say linked statically, no dynamic libraries. We first do a step over the code, over the program, looking for pointers, or looking for the entry points of the binary, okay? And then there, we take the code at that address, and we feed it to libtcg, which from the assembly code gives you tiny code instructions, and we're here. And then we translate the tiny code instructions into LLVM IR. This might sound like crazy, but it's actually one of the easiest part. So you translate from one intermediate representation to another, okay? And then you analyze what you collected, looking for new basic blocks. So maybe there was a jump, maybe there was a conditional branch, or whatnot, and you iteratively keep try to find new basic blocks, translate them to tiny code, and then to LLVM IR iteratively until you cannot find any new basic block. Hopefully you find all of them. You collect all of them in a single LLVM function, and then at this point you can link them to the helper functions that we exported with Clang before. And the final result is a single standalone binary which does exactly, which in this case, for instance, is you can compile with LLVM for x86-64, that does exactly what the original binary did. Okay? Maybe before getting to performances, I'll do a very quick demo. So we have an MD5 sum.arm binary. We can try and run it with QEMU. And it computes the MD5, nothing fancy. Then we can translate it. Sorry. We use the translate program. We let it run for a second, and in the meantime, I'll show you the performance results. So here are the performance results. These are performances taken from Spec, which is a very well-known benchmark suite, CPU 2006, only the integers one, compiled for x86-64 with GCC and O2. And we compared the performances of the native program of QEMU and of Revenge. So let's first look at those three. So you can see, so green means faster and orange means slower. So for instance, native is 6.5 times faster than QEMU, but it's only 2.7 times faster than Revenge. So this means that Revenge is 2.3 times faster than QEMU. Why is that? Because we do not perform any translation online. We perform all of it offline. So the translation time is gone, okay? We also compared it with other dynamic binary translators, which is PIN, that just works for x86, developed by Intel, and Valgrind. These are not emulators, but they are always dynamic binary translators, so they more or less work in the same way. And while you can see that we have similar performances to Valgrind, we are pretty much slower. We are twice slower than PIN. Why is that? Because PIN is very smart. PIN and Valgrind are done to perform instrumentation. So, for instance, I don't know, print the value of a register every now and then. If you don't do anything, if you do not perform any instrumentation, PIN, it's so smart that it reuses the original code, okay? So that's why it has like 30% overhead. It's very low overhead. So we tried to do the same, but actually implementing in all of these tools a real instrumentation. In this case, was just basically tracking how much distance the stack pointer traveled along the life of the program. So if you were adding something and removing something for the stack pointer, you were accumulating numbers, just random stupid instrumentation. And you can see that in this case, Revenge is 17% faster than PIN. So if you actually do something with your instrumentation, we are faster. Conclusions, yeah, so things to do. Well, try to avoid compiling everything as peak, as I mentioned before. And then I have some testing in place. This is the second iteration of this patch that I sent to the mailing list. I've been quiet for a while because I had to graduate, but now I'm going back to this. But it's hard to test certain architectures. For instance, sometimes you need a toolchain for weird architectures. So I was discussing with Riku that we should have a set of architectures, a set of toolchains for all the architecture that we support, binary that we can download and test. Okay, this would be nice. So my effort is to try to push upstream libtcg, and maybe also push upstream the ability to compile, to build helper functions and distribute them as LLVM IR. In the future, it would also be nice maybe to let QEMU use libtcg, so to reach a point where they are so decoupled where actually QEMU itself can use libtcg. This might be an idea, but we're not going to get there easily. Maybe it will also be nice to expose backends. I'm not interested in that, but maybe other people is. And it would be nice to get back FreeBSD user in shape. Right now, we've been talking about Linux, but there's also a FreeBSD version of the user emulation, which is kind of broken right now, and maybe even something for Windows, but that's crazy thinking. Okay, you can find all of this at rev.ng, and let's see if we made it. So let's try to run again with QEMU. We get that hash, and now let's try to run the translated version without QEMU, and we get the same value. So it's pretty nice, it's faster, and it's completely offline. This said, I thank you for your attention, and I'm open for questions. Yeah, go ahead. You.
Hello. When you're doing your static analysis, how do you deal with things like jump tables and stuff that's done dynamically?
Okay, so I could do a whole other talk about that. That's actually part of my research. So basically, I developed some analyses that try to mimic how you typically do that, but always in a, let's say, architecture-independent way. So we do not do heuristics. For instance, typically when you have a jump table, so if you just want to enumerate the basic blocks, which is what you need for static binary translation, you can just look at the global data and you will find the pointers. That's easy. Then you have a dispatcher, which basically at runtime says, okay, the program counter is this, then go to that basic block. But if you want to actually recover an accurate control flow graph, so when you have the indirect jump and you're going through the jump table, that's another challenge. And basically, before doing that, you usually check if the value that, so basically you're jumping at the address of the jump table plus an offset. And before doing that, you look if the offset is lower than a certain value. So basically, we prove that you can jump only in this set of addresses, and then we can enumerate all the possible destinations.
So it's heuristic. I could write some handcrafted assembler that would trick it if I tried.
Yeah, I mean, you can always do that because it's Turing complete, right? If you jump, if you give control to the user, to the program counter, you're done. I mean, there's a fallback solution, marking all the possible bytes within the executable segment as basic blocks. But that's really bad. So you have to get to a trade-off there. Say it again?
That still wouldn't work if the thing you're trying to deal with is...
No, I had a backup slide about that. We don't do that. That's my backup slide.
So you've got something and it won't actually work for the whole universe code. So that's why you have to do this dynamically.
Yeah, I mean, in theory, you could do this dynamically, but it's not of our interest, and it will be crazily slow. Other questions? Go ahead.
So what I'm reading is you're not possibly interested in some concolic form of execution to try to enumerate these things. You would just want to go purely static, and I guess it kind of makes sense as well, because when you look at modern programming languages, they kind of really do discourage playing around with lots of different bits, I guess.
Yeah, I mean, I can say that, for instance, we can, well, running patch benchmarks, we never miss any basic block, okay? And the accuracy of the graph that I can link you the papers, but for instance, we are also able to handle what the mem set for ARM in uselibc does, and it does some really nasty tricks in handwritten assembly. Obviously, we cannot cover all of the possible situations because it's too incomplete, but I think that we can cover all of the code generated by compilers and a large set of what commonly happens in handwritten assembly. But symbolic execution, or concolic execution, that's something that we considered, but there are already solutions doing that. For instance, there's angr, it's another binary analysis framework. Point is, they say, okay, our solution is perfect. You know, we find everything. The only point is that when your binary starts getting bigger than a certain amount, they say, okay, we have the fast version of this, which does not use symbolic execution, and it's heuristics, basically. Sure.
Sorry, we are running out of time.
Yeah, you can come to me and be more than happy to answer. So thanks again for your attention.